Hi, welcome to my talk on Extensible Records and type-indexed maps. So, you may know me. I'm Christopher Vogt. I worked on Slick before. I recently joined a company in New York, x.ai, and we're building a personal assistant for scheduling meetings. So, if you have a lot of meetings, then basically, instead of going back and forth by email a lot yourself, you can just CC our agent Amy, and Amy takes it from there, and you'll get the invite in the end. So we do a lot of data science, natural language processing, and the data scientists work a lot with ad hoc data, and I try to find some solutions for them to be more productive with like ad hoc structures they can work with, but also some stuff that just helps in general, like working with data every day. So I was intending to call this talk Scala Records until I noticed that there's already a project, Scala Records. So I'm calling it Composable now. And type-indexed, extensible records and type-indexed maps. Why should you care? That's what I'll talk about. And how to use them by examples and how they're implemented under the hood. Looking at some macro stuff and some type level stuff. And we'll also compare them to other implementations out there. So extensible records are somewhat like anonymous classes on steroids. They're similar to the whole new braces thing. Put a couple defs in there you may have seen in Scala. So you can ad hoc create structured data, type safe. However, the composable implementation doesn't need reflection like the Scala ones. Also, one of the main motivations for me to work on this was that I want to have type safe, concise transformation on structural data, on type safe structural data. You know copy from case classes, right? You can create something else with the same structure, keep some parts and replace something. But you can't do that when you have like two things that are somewhat similar but not exactly. You want to go from one to the other. It's a lot of manual overhead for that. So I implement something like copy, but also things like ++ where you can compose them, like merge them. Basically that's like the big pain example, but let's look at that in code immediately. So let's assume we have a case class email. Well, we're processing a lot of emails, right? x.ai. And we have another class full email that has some more data, because in some case we need that, and in the other case we need the other thing. And if you want to create an instance of the email, and then you want to add more data because you found it or in your current situation, you kind of need to copy the other stuff over, which is not ideally what you would want. So what you can do with records instead, well, let's just run this for now. So this will print an email, just like that. So what you can do with a record is you can say, hey, val r equals record body and then just ad hoc, without creating a class or something, created a structure just like that has these fields, and you can access them. If you access something else, it will give you a type arrow. But what you can also do is something like val r2 is my original record, but you add some more fields to it by just composing it with another record, and one that has a subject, let's say, and another date for the received date. Cool, so let's look at R2. So that's that. One thing I wanted as well is interoperability with existing Scala features like case classes. So you have this, you can do that either explicitly or you can import this conversions thing, and then you can basically say stuff like, well, let's not use this, let's just use the email here. And you get a record out of it. Or I don't want a record, I want a full email that structurally matches my record. And you get that out, and it will basically just name match. This goes in here, and the stuff from the email goes in where it matches, and so you can just work conveniently with transforming data. That's the, oh yeah, and it's also interoperable with Scala's native structural types. So, same thing. What you may have noticed is that we didn't get any warning for like reflective access, which is what you normally do when you work with structural types in Scala. So if we do this and access the subject here, we will get S. We will get a reflective access warning. However, the composable records get away without reflective access. And I'll show you later how that actually works. All right, let's get back to the slides. So what operations do I have? I showed creation already, but I'll be a little quick on these slides. So composable records use Scala structural types as a type argument to describe what the record looks like. That means that the structural type is actually easy to write because you just write the Scala type. And it looks very similar. And, well, you don't have reflective access. There's no 22 field limit. You can just, well, there are some limits of the JVM, but they're much higher, like with, it supports copy, like case classes do. You can merge them, I showed that. You can convert, the slides are more like backup. I wanted to show it all live, if possible. You can convert from them explicitly. Well, like you can look at these slides later. You can have the implicit magical conversion. Yes. Oh, and another feature, something that you would need in a database setting. I didn't make this stuff work with Slick yet, but it's my plan. Sometimes you have a larger structure like a case class, and some aspect of your program you just want like some fields. What you would normally do right now is you create a tuple, but you lose the names, right? Sometimes it would be nice to keep the names. So with the composable records, you can do something like this. Let's say from this email, I only want the subject and the body, so I can say, so I have this DSL right now. I'm not completely happy with that, but you can say basically subject and body. And when you print this down here, you get a record that just has the subject and the body. One thing that's important to point out is that, so I'm using macros to implement those things, and there are these two different types of macros, white box macros and black box macros. And black box macros are the ones where the signatures of all the involved methods completely tell you what's happening on the type level. And that also means that tools using Scala who don't have the full compiler but only reason about the types on their own, which IntelliJ does, for example, can reason about black box macros, but they can't reason about white box macros unless the signatures are precise enough to reason about what they need. So some features are only available as white box macros, but most of the stuff is actually possible with black box macros. So this creation I showed you is not. But I'm offering an alternative syntax where you basically just put a structural type in there. And then if we're working with IntelliJ or something, you get code completion. Same for select. So an alternative syntax I have for select is, you can just say, hey, give me something with a name. Well, in this case it's subject, right? Subject and a body. And you will get these fields. And this way you can, while you're processing data that consists of more fields, you can just kind of take the ones you need and keep the names and just continue going. All right, select. Black box fallbacks, talked about that. Right, JSON serialization. So let's see. I'm going to copy something over from here, this string. So one thing that we have a lot in the data science work is that we just get some data out of our database. We're working with Mongo there, and then people want to work with certain parts of this, and people kind of want to more or less ad hoc, the data scientists want to more or less ad hoc decide what they need and work with it. And often people fall back onto dynamic access into JSON objects or something like this. Can we take questions at the end, please? Yeah. And basically, this also allows you to ad hoc select what you need and then work type safe from there. So I implemented a JSON deserializer for play. And let's all right, let's see, what do we have here? We have, well, one of the fields is age. Let's keep the age. And one of the other fields is addresses. And addresses, again, is a sequence of stuff. So let's say list. And list of records again. And what do we have in there? Well, city, zip, street. Let's take the zip code. And let's take the street. And then oh, it's S, I think, in play. Sorry? Oh, right, I have to say record here. Yeah, that's correct. Thanks. So that works, and I get a record back that matches the structure. And I can work with the type safe, right? I can say something like addresses 1 and dot street or something. And there I get the address of the Scala lab in Switzerland. Cool, so you can ad hoc make up these structures, and that's not always the best thing to do. Often you want your data model fixed, described in a single place. But when you are working with very exploratory code and like working with ad hoc things, this can be nicer than working fully dynamic. All right, so what's left to do? Some simple stuff I didn't implement yet, like structural comparison of records, which should be simple to do, but I just didn't get to it. Structural pattern matching, which would probably be really nice to have, like just select certain fields and match on that. Also, if you look at the word record now, it would also be nice to do the same for case classes, right? Have a case class and structurally match on this case class. Depends on your use case. In some cases, it's really nice if your client code breaks when you change the fields in the case class. But in some cases, like for example, let's have a case class that has lots of different constraints, and you want to make sure that at the calls, like at the user side, you use all of the constraints, and when somebody adds a new one as a field, then you want to detect that place. But in other cases, like when you process emails, for example, when you want to find like some occurrences of words in the body or something, you don't care if somebody adds another header or a date or something. So then in this case, it would be nice to not have your matching code depend on the structure, like the parts of the structure you don't need. Rename. Records for me are a lot about, I mean, for collections, we have all these nice operations, how we can do transformations from one collection to the other. But on structured data, on the things that are usually the elements of these collections, we don't really have that in Scala at the moment. We have to do a lot of manual work, and it would be nice to have, well, let's say if we have one class that has a field last name and another one that has a field surname, and you don't want to mention all the fields of the class just to kind of copy from the one to the other and just rename the field, basically. So something like rename would be desirable, and removing fields just to describe transformations on records or in structured data. Also, one thing I want to do still is integrate that with Slick, because in Slick, You also have the problem that often you select certain fields, and when you do this right now, you'll get a tuple and the names are gone. Also, the records concept of merging records fits very nicely with the concept of joins in databases, right? So you would get them in the same structure. Yeah, and one pattern you could use is, well, if you describe a record, a type alias for a record, you could have an implicit class on that thing that adds methods. So it's very much like a class in that sense, how we can work with it. All right, other implementations. So there's Shapeless, and Shapeless has Extensible Records, and it's probably the most mature and complete implementation that's out there. Shapeless is based on h-lists and string singleton types, and for using the h-list, Shapeless uses implicits extensively. The nice thing about it is that it's a very clean theory, and it's in principle it should have full code completion for everything. There is, however, a compile time overhead which you can't get away from, because these implicits rely on the implicit search and the implicit resolution of the compiler, and there's nothing the library can do about how fast or how that works. Also, the types of Shapeless records are not human writable, if I'm not mistaken, and there are some ways to get them, but there's some trickery involved. Also, it's just Scala has a record syntax and like the structural types basically, so you could use them. I'm sure Miles has some comments about that later. Cool. So there's another project regarding records at EPFL actually. And I had a long discussion with one of the guys who are working on this on the weekend, long productive discussion, and turns out they're very similar to what I'm doing, but most of the stuff that's implemented is very complementary. The only overlap is basically how we represent the structural types within the record. So as you've seen, I've represented them as a type argument with a structural type. What Scala Records does right now is that it has a refinement on the record. So it generates a subclass, an anonymous subclass of record every time you create a record, and goes from there. However, these types, well, if you write these types, then either you get back to structural typing with reflection, or the trick that they are doing is the vampire macros, but then again, you can't write down the types at all anymore unless you use some trickery. Also, they rely completely on white box macros, so there's no code completion in something like IntelliJ. However, something really cool that they're doing is their record, so the composable records internally just have a hash map. They're just internally hash maps, and you do hash map operations. The Scala records are basically just type-safe views on existing data. So you don't need to copy anything into a map. You just have basically a type-safe layer on top of it and access directly what you need. And it's extensible with regard to the backends. They have an implementation with a hash map, just like composable, but they also have one for Spark records, I think. Yeah, and looks like there's very little overlap, only in this one place, and there's a good chance that we'll merge the efforts and kind of get everything, because they didn't really focus on transformations, which is the big thing for me, but yeah, seems to be complementary mostly. Yeah, so this stuff didn't exist yet at all 6-7 weeks ago or something. But I am hoping to stabilize the core of it soon, because I just want to start using it in production. And the nice thing, what I like about this implementation is that it has a very familiar syntax with the records and the structural types in there, and it's as fast as we implement the macros. So if we do a good job at the implementation of the macros, there shouldn't be any performance obstacles that are not up to us. And it's mostly black box macros, so you get code completion. There's some places where you don't have black box macros, but they are rare. Yeah, that's records. So another thing, and that actually the records are like a spin-off out of this idea, are these type-indexed maps. And basically the idea is that you can use intersection types, so A with B with C, to represent sets of types. And what you can do with it, basically you can have a sort of type-safe map where the types are the keys, or you can use it to track dependencies or track effects. And well, the simplest The simplest thing you can do is this. You create a new T-map, you get throw an object in there, then it becomes a T-map of the type of this object, and then you can get it back out. It's a map. The next thing you can do is you can compose them. So here we throw a string in, and we put an int in, and then we get one that has a string and an int, and then we can get both of them out. Let's implement one. So let's see. So simplest thing we could do is just create a new one, right? So here I have like a rough structure, and we just need to fill in the apply method of the companion. And basically what this apply method takes is a value you want to put in, and for this value it takes the type tag, the Scala reflection type tag, because it needs this as the key to look it up later again. And the T-map itself is, well, it stores the type of its elements, and it has a list in there which are pairs of types and values. So to create a T-map, well, we're creating one, give it the type that we found, and we put a list inside that is the type of the type tag, or the type stored on the side of the type tag, and that maps to the value. Cool, so the creation should work now. Yeah. Cool, didn't print anything yet. Now what we want to do is we want to look stuff up again. Let's look up the string that we just put in. So we need to implement lookup. Lookup is an apply method in this case on the T-map itself, and it again takes the type tag of what you're looking up. And then, well, you need to look in the values, find the type that is the same like the type you're looking up. How? Oh yeah. Thanks. So, however, you shouldn't be allowed to look up anything. You should only be allowed to look up things that are actually inside the type index map. So we need a constraint here that says that this Q we're looking up is actually a supertype of the elements in the list. Think about it, like if the map contains a string and an int, the type will be T-map of string with int, and then you're allowed to look up an int, which is a supertype of that. Int is a supertype of int with string. Even though you can never have an object or a value of type int with string, it's still a valid type on the Scala type system. You can express it as a type, it's just you can't have a value. But you can use it as a phantom type in this argument of T-map, where you just kind of carry it around. If you use it here. Yes, I'm getting into that in a little bit. So, yeah, so we find it, we assume it's in there because it's a supertype, and then we get it, and then we take the value, and then we need to cast it back to the queue. All right, let's see if that works. So we are assuming we can get a string out, and it matches the one we put in. Yeah, it's the other way around, right? Cool. Well, didn't fail. Let's put some bull. Cool, that does fail. All right. Valid question with the any-val. If you do ask for an any-val here, it will currently crash. Or it will currently, no, let's ask for an any. Okay, it doesn't crash because we're asking for a string here, but if we just ask for an any here, it will crash. Because any is also a valid supertype of whatever you have in there. So we need to kind of do something about that. And to do that, we say, hey, let's not just find something that matches the type, let's find anything that's a subtype of that, which makes it sound. So let's print whatever we get out of here. So, well, you asked for an any, you got an any. It's maybe not what you wanted, but it's sound on the type system level. If you use, and the use case, well, the use case that brought me to type-indexed maps is actually dependency injection. In case of dependency injection, this shouldn't be a problem, because you're not usually asking for like a super type of a database or something. You're having a database and a logger and a cache in there, and you want the one. However, for other use cases, it's a valid problem. And one thing I'm still planning to work on, basically having macros that check if, well, things are valid, so that they prevent something like any. And there are other operations when you do merges or when you do, where you need to basically check that, or also when you upcast your whole map to something. All right, let's continue. So that's working. Let's make the merging of TMaps work, and records work very similarly under the hood. So we have a tmap, and we take another tmap as the argument, and now we want a new tmap that has the values like the types of the first one and the types of the second one, and has also the values of both, right? Cool. So we should be able to look up, merge them and look up both of the things. And that worked. So what else can you do with tmaps? I mean, the type-safe map thing is nice, but there's something else you can do with it. And my use case was dependency injection. So you can track dependencies of parts of your program and propagate these dependencies automatically. So let's say we have a logger, and that logger has a method log that takes a message, and let's implement that using just print line for now. And let's say we have a database, and it has a method query, and that takes the query and returns us just hard code something. Cool. So and now I'm writing modules, and actually these modules are just functions that take, let's say, a database and do something with it. And another one that takes logger. And log something, right? And what I would like to do, that I have basically components of my program which need certain resources, and I kind of want to put them all together, and in the end, at the outside somewhere, create all the resources and just pass them through my program, but still can reason about what needs what and make assertions of type checks about that. So what I came up with are these tmaps. So basically, I'm writing a method that basically converts something like this into a new function that, instead of taking a database directly, it takes a tmap of a database and then pulls it out of there. So I call this diffuse, and it takes a t. It takes a function from t to the return type r, and returns a function from a tmap of t to r. And how it's implemented is basically, it takes a tmap of t, and it calls f on the value that you get out when you, and you need a type tag for that, because the map needs a type tag. So you can just say use a database and use a logger. And now you can, let's not compose them, let's first just use them. So we can create something that holds all the dependencies. We can put a new logger in there and new database in there, and that could be something from some libraries, right? It could be like a Slick database or something. And now we can call M1 of depths and M2 of depths, and that just works. It should. No type take available. All right. Yeah, there's a problem. Classes that are defined inside of functions, inside of lambdas, don't have class tags, so I need to pull them out to the top level. And is there something else? Right. So right now TMaps are invariant, which means you can't use a tmap of logger with database in a place where you need a tmap of a logger. So we need to change that and make the tmap covariant. So we'll just place a plus here. And now it works. Yeah. Cool. And now we pull the good old reader monad out of the pocket, this one. Or you can take it from Scala Z, which works equally fine. And this just extends functions, in this case even functions from tmap, but it works also if it's not tmap. So the types are slightly nicer if you write tmap here, and makes them composable with comprehension. So basically what you can do is you can say, I want a new function that does what M1 does and what M2 does and produces some result. And to get this, I just say, hey, for, well, M1 produces people, and M2 produces nothing. It's just a side effect. And I want to compose those together into a new function that basically takes the arguments of both merged, the tmap of a logger and the tmap of a database kind of together into a tmap of logger with database, and then yields the people. So now you can say M12 of depths and it will give you both things. And the nice thing about it is that the dependency are automatically propagated because they are part of the return type. So even if this thing takes another dependency, this will just get it. You don't need to change the code of the function that compose it. So in a way, it's like implicits. So I basically kind of partially implemented implicits as a library in Scala, so stuff propagates. And I'm pretty sure you can use it exactly for what Martin talked about in the keynote, where you basically track dependencies, tracks effects in the same way. All right, so these are TMaps. And tomorrow there's a talk by John Pretty where he uses TMaps, this guy, where he uses TMaps for tracking error states of results, right? Exceptions, yeah.
So I have multiple possible types of exceptions that may result from some operation, and I use the intersection types of some number of exceptions. It's basically a TMap.
Cool. So another problem we have, and that's the problem Miles basically talked about, a covariant tmap and subtyping are a problem because you could look up elements, but basically, well, you could look up an element that doesn't exist, or you could kind of merge tmaps with the same elements and you kind of, one sort of disappears, or you could upcast them because now they're covariant, we just made them covariant, and you could lose information. But the solution to this would be making them invariant, but having conversion macros that do only the conversions that are valid. So basically just, you exclude certain cases that aren't, and this way you can basically use intersection types really as type sets. Because this, just like this, we're kind of misusing them, right? They don't have only the property that you kind of can throw them together into something. They also have the subtyping relationship, which is the problem. All right, let's look a little bit behind the scenes because there's some funny stuff going on. So the records use structural phantom intersection types and macros, and let's see. So structural types, you've seen structural types before, right? Cool. Phantom types is if we basically just put a type in a type argument, but we don't have anything that actually has this type as a Scala concept. There's no method or val or something that really uses this type. So in the case of the T-map, yeah, there is an integer in this map, but this map has types, or in this list, but this list has type like a list of type and any, or in case of the record, there's like a map in there as well. So we're just tracking, we're just using this type argument to track it. And we'll spend a little bit of time on this slide, but this is how basically my records implement structural lookup, or lookup in the structural type without reflection. So the record itself has the structural type as a type argument, and there is an implicit conversion that converts from this record to the actual implementation of the structural type, like to an anonymous class. And down there's like the steps that happen. So if you do r.name, what actually happens is an implicit conversion is applied because record itself doesn't have name. So the materializing conversion is applied, which returns a t, which has a name. However, this t is a anonymous class, which again has macro members. So it also has a reference to the map of the record. So if the record has a field name, then this anonymous class will have a def name, which is a macro again, which does the lookup. And lookup is another macro, which will just basically look, hey, what was the name of what I'm called? And then just does a reference into the map of the record. And in the end, you only have maps. The only thing that remains at runtime are maps. You basically pass maps around, but you have the whole type safe checking on top of that. One thing that's interesting, when you merge two records, like a record of T and a record of Q, the way ++ is implemented is you will have a record of T with Q. And that's slightly different from what you may have expected, because it's kind of the one structural type with the other structural type, which you can't even write down in Scala because the parser doesn't buy that. You can kind of pull them out into aliases and then you can write it. But what you would actually expect it is this. Like you have one structural type that has both of the things. But as it turns out, intersection types, intersection type themselves are like you have a type A and type B, and A with B is a subtype of A, but also a subtype of B. But when you combine them with structural types, A with B is actually the same like the merged one. It's subtypes in both directions, equivalent. So, yep, you can write it like that, and that's fine. Even if record was invariant, you could still write it like that. Same thing for TMaps. So, if you use the reader monad from Scala Z, it's something that's agnostic to TMaps, to compose them, you will get these tmap of A with tmap of B, which is not really what you expected, because you wanted a tmap of A with B, like a tmap of a logger with the database, not like... however, again, so that's what we kind of were looking for. As it turns out, if tmap is covariant, which it is in our case, then tmap of A with B is a subtype in Scala of tmap of A with tmap of B. Assumably because tmap of A with B is a subtype of tmap of A, and tmap of A with B is a subtype of tmap with B. So yeah, it's a subtype of the two together. And now if you use that in functions like we did for the dependency injection, they are contravariant in their arguments. So the relationship is turned around. Right down there, the tmap of A with B to some x is a supertype of tmap of A with tmap of B to some x. So when the Scala Z reader monad would produce something like tmap of A with tmap of B, we can upcast that to this and use it when we just annotated this. And it just works, and that's cool. So records allow nicely to ad hoc create type-safe structured data and work with it with transformations. And TMaps use the same concept or a similar concept to track, or to have type-safe maps with values to track dependencies, track effects, and infer them, and then basically propagate them through multiple calls. And I want to thank the Scala Records team, because several times I kind of looked into their code, like, how did they do that? And then there were like some kind of crazy cool hacks with macros that kind of makes them with something weird work. Also, I had a super helpful discussion with Tobias, who's over there on the weekend, which may lead to like us joining forces basically. Also, I want to thank Guillaume Mercier, because we coded after any Scala on this, like on the TMaps stuff, which was quite helpful. And John Pretty for basically kind of pushing me to look more into records, which, well, he said look at string singleton types, and I did, and I implemented it, it works. Then I was like, oh, there are structural types, right? So, and then I kind of moved on from there. Yeah, and if you want to work with like a strong Scala team in New York City, we're hiring at x.ai. Thank you.